The purpose of this screencast is to review how to calculate net driving force and interpret the results. Recall that net driving force is equal to the memory potential minus the equilibrium potential for an ion. Let's say an experimenter changes the memory potential of a cell to minus 100 millivolts, and we want to determine the net driving force acting on potassium. We know that potassium's equilibrium potential is minus 75 millivolts. So we have that the net driving force acting on potassium is equal to the memory potential, minus 100 millivolts, minus the equilibrium potential for potassium, minus 75 millivolts, which gives us a net driving force acting on potassium of minus 25 millivolts. So we have a negative net driving force. This tells us that the direction of net current flow is inward. In other words, the direction that positive current would flow is inward. Thus, we also know that the direction that potassium will flow is inward, since it's a positively charged ion. Another way to look at this is that potassium will be at its electrochemical equilibrium when the memory potential is at minus 75 millivolts. So potassium will flow to try to change the memory potential from where it's at, which in this case is minus 100 millivolts, towards potassium's equilibrium potential. Thus, in this case, we'd have a net flow of positive charge into the cell to try to change the memory potential from where it's at, minus 100 millivolts, towards potassium's equilibrium potential of minus 75 millivolts, and thus we would have potassium flowing into the cell to produce this change. On the other hand, if the experimenter changes the memory potential of the cell to minus 50 millivolts, we have that the net driving force is equal to negative 50 millivolts minus potassium's equilibrium potential of minus 75 millivolts, which now gives us plus 25 millivolts. So in this case, we have a positive net driving force. This tells us that the direction of net current flow, or the direction that positive charge would move, is outward. And thus we also know that the direction that potassium ions would be flowing is outward. Again, another way to look at this is that potassium will be at electrochemical equilibrium when the memory potential is at its equilibrium potential of minus 75 millivolts. In this case, the memory potential is at a more positive memory potential, minus 50 millivolts. Therefore, potassium will flow outward to try to change the memory potential from where it's at, minus 50 millivolts, towards potassium's equilibrium potential of minus 75 millivolts. Now let's consider the case of an anion, such as chloride. If the memory potential is minus 100 millivolts, and chloride's equilibrium potential is minus 70 millivolts, then we have that the net driving force acting on chloride is equal to minus 100 millivolts minus chloride's equilibrium potential of minus 70 millivolts. This gives us a net driving force of minus 30 millivolts. Here again we have a negative net driving force, and this again tells us that the direction of net current flow, or the direction that positive charges would be moving, is again inward. However, if we want to know which direction chloride ions are actually flowing, it would be in the opposite direction. If chloride ions are flowing outward, it would have the same effect on the memory potential as if positive charge were flowing into the cell. Another way to look at this is that chloride will be at its electrochemical equilibrium when the memory potential is equal to minus 70 millivolts. So if the memory potential is at minus 100 millivolts, chloride will actually leave the cell in order to change the memory potential from the more negative minus 100 millivolts towards chloride's equilibrium potential of minus 70 millivolts. And thus the inside of the cell would be becoming more positive, as if positive charge were moving into the cell. That concludes the screencast on net driving force. If you have any questions, please bring them to recitation or office hours.